Hi, hello, welcome back. This video is all about power amplifiers. Okay, so to start with, we have here different classifications of amplifiers. Okay, so we are under linear amplifiers. So linear amplifiers are classified according to the following mode of operation. So the first classification of an amplifier is as based on its input signal. So as based on its input signal, we have here your small signal amplifier and we have here your large signal amplifier. So what's the main difference between the two? Those amplifiers that we are discussing previously, they are mostly under the small signal amplifier type. So these types of transistor amplifier are just limited at the almost center of the active region. Okay, so we place an input signal that is not large enough, so this is small enough just to be maintained around the center of your active region. Okay, but when we say large signal amplifier, your input signal is large enough that it can reach your saturation and your cutoff regions. Okay, so that's the main difference. So it is not something like it is 1 milliampere a small input, or is 1 volt is a 1 millivolt a small input signal and a 1 volt is a large signal. Actually, it's not on the numerical value. It's on the fact that if your signal stays within the center of your active region and it is free of distortion, therefore we are dealing with small signal amplifiers. But if it uses up to the saturation and the cutoff regions, therefore we are dealing with large signal amplifiers. Okay, so the next classification is based on its output. Okay, so when we are looking for the relationship between the output voltage and the input voltage, then we have a voltage amplifier and we are defining the voltage gain of that specific amplifier. But if we're concerned with the output power with respect to the input power, then we are talking about power amplifiers. Okay, so mostly those being used in communications or sound systems, usually they are classified as power amplifiers, because if we buy some speakers, for example, or amplifiers, for example, so it is rated in terms of wattage instead of voltage. Okay, so again, is based on its frequency response. It can either be audio frequency amplifier. So we have already discussed frequency response from our previous videos. So if your amplifier is capable of amplifying frequencies that falls under the audio frequency range, so normally they are made up of um, low frequencies in your frequency spectrum. So therefore, they are termed as AF amplifiers. Okay, so there are frequencies that are being used in communications, particularly in AM or FM or TV broadcasting. So they are called intermediate frequency. So intermediate frequencies are lies somewhere between the modulating signal frequency or the audio frequency and the radio frequency. Okay, so usually we use this in frequency translation so that we will not abruptly change your frequency from a very high value to a very low value. So sometimes we will have a middle frequency. So that middle frequency is what we call intermediate frequency. So we will be dealing with this in our communication subject. So each communications applications like AM, FM, and TV broadcasting, they have their own intermediate frequencies. Okay, and then of course RF. So this is the frequency range that most carriers are under. Okay, so we usually define high radio frequency amplifiers for us, those amplifiers capable of amplifying signals with high frequencies. And then we have another classification here based on its biasing conditions. So this is where your class A, class AB, class B, and class C will come into place. So we will be dealing on this types or in this category in this video. And then of course you already know the basic transistor configurations for BJT. So we have your common base, your common emitter, and your common collector configuration. Okay, so in describing a certain amplifier, it is just normal if we describe them based on this different classification. So for example, we have a small signal class A common emitter voltage amplifier. Okay, so this is like somewhat a very very exact description for our amplifier. Okay, so you can determine what type of amplifier is that by stating their characteristics. So we have here the comparison of amplifier configurations. Okay, so this common base, common emitter, and common collector amplifier configurations are the basic building blocks. Okay, so we have discussed compound configurations wherein, just like in cascaded amplifiers, we usually combine one, two, or more of these basic building blocks. Okay, so we can if we wanted to have a higher gain, we can cascade two common emitters. Okay, so usually the common base and the common collectors, they come together because of what we call impedance matching. So common base has a characteristic of a very low, or so it has the lowest input impedance. So therefore, to compensate for that, we usually place a common collector which has a characteristic on the other side as the highest input impedance. So we usually place common collector before common base. Okay, so to compensate for the characteristic of common base having the lowest input impedance. Okay, so in this table you can see their basic characteristics. Okay, so this is very useful. This is being asked. Many questions regarding these tables are usually asked in some multiple type of exam in the summary of each book. So you have to be very familiar with these characteristics of the single stages, common base, common emitter, and common collector. Okay, so your amplifier action depends on low power input circuits controlling the high power output circuits. So here are the basic characteristics of the three basic configurations. So common base is described as the low impedance emitter circuit, which absorbs less power as compared to that which is available at the high impedance collector. Okay, so for common emitter, this is the low base current flowing gives rise to much higher collector current flowing out of the high impedance output circuit. And then finally, for common collector, we do not usually make use of the common collector as an amplifier because technically it has a unity gain for voltage amplification, but we usually use this for impedance matching as an impedance matching device. Okay, so this requires a low input current to control much larger output current. So it has only low input current. Why? Because its characteristic is having the highest input impedance. Okay, so amplifier classes, this is based on the amount of transistor bias and amplitude of the input signal. Okay, so this takes into the account the portion of the cycle for which the transistor conducts. So we have here 360 degrees conduction, we have 180 degrees, low below 180 degrees, and so on. So we will be discussing this later. And it represents the amount of output signal varies over one cycle of operation for full cycle of input signal. Okay, so we are dealing now with large signals. amplifiers. So from our previous videos, from your electronics one, those are small signal amplifiers. Okay, so we usually deal with very small amount of currents, usually in milliampere ranges or even microamperes when it comes to the base current. Okay, for now, we will start discussing those having large signal or what we call power amplifiers. Okay, so this provide sufficient power to an output load to drive a speaker or other power device. Because if we will just make use of your small signal amplifiers, there's a tendency that we might not turn on your output load. So for amplifiers, usually, so it has something to do with sounds. For example, our load is usually in a form of a speaker or headphones or earphones. Okay, so for bigger speakers, okay, so small signals might not be enough to operate them, so therefore we will be needing large signals in the form of power amplifiers. Okay, so these are amplifier circuits used to handle large voltage signals at moderate to high current levels. Okay, so in this type of discussions, we will be having additional items, additional parameters, okay, that were not discussed before in our previous videos. Okay, so what are those? So we are now concerned with circuits power efficiency. So later we will be defining what is power efficiency, and then we have your maximum amount of power that the circuit is capable of handling. So this is the maximum power that the transistor, okay, we call that power transistor, that your power transistor can dissipate. And we will also be dealing with the impedance matching to the output device. Although we have already mentioned from the previous videos what it is meant by impedance matching. Okay, so let us start with the power efficiency. Okay, so to determine the power efficiency, we will be needing the following. Okay, so we will be needing the DC power supplied to an amplifier by the source. So your PDC or the DC power is equivalent to your DC source, which is your VCC if we are having a common emitter configuration. And we have here your IDC or your IQC. Okay, so this is your DC current and this is your DC voltage. So your efficiency is used to compare the design of power amplifiers, particularly having the highest or a higher frequency means a better design of your amplifier. Okay, the higher the efficiency, the better. So this is our symbol for efficiency, okay? And it is given by the formula P out. So this P out here is the AC output power divided by the DC input power. So your P out here in the numerator is an AC power, while your DC here is a DC power, or the total DC power supplied by the source. Okay? So the main concern here is how much AC power will be converted from your input DC power. Okay, so our purpose is to convert or to what do you call this, to produce an AC power out of your DC power. Okay, so power efficiency, this is a way to compare two different designs because it indicates how well an amplifier converts the DC input power to an AC output power. Okay, so the power efficiency lies between 0 to 100%. 100% is said to be the highest, so it can never be greater than 100 because you cannot have an output that is you cannot have an output AC that is greater than your input DC. Okay, so usually 100% is purely theoretical, because it means that all of the DC input will be converted into an AC output power. But in reality, when you connect your circuit, when you build your circuit, you have components within it. Okay, and those components, even resistors, okay, or the transistor itself, they tend to dissipate heat. So as they tend to dissipate heat, those that heat is considered as a power. So it is already considered as a power loss. Okay, so once your resistor dissipates heat in a form, a power in a form of a heat, automatically that is lesser than the total input power. So therefore 100% is really purely theoretical. Okay, so because if we have a 100% efficiency, that means your system is totally lossless. Okay, and there is no such thing as a lossless system. So the higher the efficiency, the better the amplifier is at converting DC to AC power. So we can see this importance, okay, in the battery operated equipment. So for example, uh, you have a toy, okay, so a toy car, for example, or a helicopter or an airplane that is a battery operated device or toy. Okay, so you will be needing a nicer or a better battery to operate that. So if you will just be using a normal battery or those low cost batteries, maybe you can just use it for a certain for a very short period of time. But if you will be using batteries just like energizers or ever ready gold like that, so you can use it for a longer period of time. So that is meant by efficiency. So those batteries that you can make use of in a longer period of time. So that is those are the batteries having higher efficiency compared to the low cost batteries. So for the low cost batteries, maybe you can make use of them in the remote controls of your televisions or your electric fans or something, or doorbell like that, but not for uh battery operated equipments. Okay, so these are the comparison of amplifier classes. So they can be classified or they can be compared in terms of their operating cycle. So we have here your class A, your class AB, your class B, your class C, and your class D. Okay, and with respect to their power efficiency. So as you can see, power efficiency and operating cycle is technically opposite. Okay, so the lesser your operating cycle, it will give you the higher power efficiency. Okay, so for class, usually we use class A to class D in analog applications. So class D, it's not technically for digital, or it's some thinks that this D is for digital, although it is already composed of pulses. Okay, so very small pulses. Actually, your class C is already in the form of a pulse, and pulse is usually being associated with digital applications. Okay, but class D amplifiers are usually those typically over 90% efficiency. So this is those are the things, these are the types of amplifiers that has a very high efficiency. But for this discussion, we will be for this video, we will just be dealing with those amplifiers that are used in analog communications, and that is up to class C amplifiers. Okay, so we have here different types of coupling. We'll just do this fast because we have already discussed this from our previous videos. So there are what we call capacitive coupling, when we use capacitors to couple your first stage to the next stage of your amplifier circuit. So the coupling capacitor transmits the amplified AC voltage to the next stage, just like in this figure. Okay, so we call this AC coupling. So usually this is used for AC amplifiers, and usually usually this capacitor here sets the value for your lower cutoff frequency. Okay, so in your frequency response, this capacitor here is the one which is responsible for your lower cutoff frequency. And since this is an AC amplifier, it blocks the DC voltage, because DC voltage, as we all know, starts with is equivalent to 0 hertz. And since we have a low frequency, so therefore we have a low frequency cutoff, so therefore it blocks your DC voltage. Another way to couple your first stage to the next stage is by using transformer, or transformers are in a form of an inductor, okay, or a form of inductor, which is your transformer. So the AC voltage is coupled through a transformer to the next stage. Again, your L is also frequency dependent, okay? So therefore, your transformer here, or your inductance here, will also serve as your uh, lower cutoff frequency. So it will be the one to contribute to your lower cutoff frequency. And since you have a lower cutoff frequency, we also call those circuits using transformer for as a coupling device as AC amplifiers. So thus, just like the capacitor coupling, they also blocks your DC voltage. Okay, so the third type is direct coupling. As you can see, you connect your first stage to the second stage directly. The output from the collector of your first stage to the base of your second stage. Okay? So since we don't have a capacitor here, or an inductor here, or a transformer here, so since they are directly connected, um, no your lower cutoff frequency will not be dictated by a capacitor, or likewise a transformer. So therefore, these are what we call DC amplifiers, wherein there is no lower frequency limit. So technically, you are starting at 0 hertz frequency. So therefore, we call that as a DC amplifier. Okay? So these are the three ranges of frequency. Actually, your audio amplifier, so it is capable of amplifying those frequencies in within the range of 20 to 20 kilohertz. Okay, so this is what we call your hearing range, normal hearing audio hearing range. Okay, so RF, on the other hand, one that amplifies frequencies way above. Okay, usually higher than 20 kilohertz. Okay, so as I've mentioned earlier, between the audio and the radio amplifier, we will be having an intermediate frequency. Okay, so we will be dealing more on the intermediate frequency in our discussions regarding amplitude modulations and frequency modulations. Okay, so we have here two types of amplifiers. We have a narrow band and wide band. So as the name implies, narrow, that means we have a very small frequency range. Okay, so usually narrow band amplifiers are called tuned RF amplifiers, or radio frequency amplifiers. We usually use this for RF, okay, ranges, radio frequency ranges. Okay, so tuned amplifiers, their AC load is a high Q resonant tank, okay, or we call this as a tuned circuit. Okay, so this is tuned to a specific radio station or television channel, because when you have a radio station that is very limited in terms of its bandwidth, so we have to create a circuit that is only tuned for that specific range of frequency. Okay, so quality factor is inversely proportional with the bandwidth. So when we say you have a high Q, or high quality factor, that means we have a narrow bandwidth. Okay, and usually for tuned RF, our load is in a form of a resonant tank. Okay, so it is not resistive. For wideband amplifiers, the opposite of narrowband amplifiers, so usually narrowband amplifiers are used to tune a radio or television channel. So wideband amplifiers, they operates over a large frequency range, so we call this untuned. Okay, so their AC load is purely resistive, while the AC load here is made up of resonant tank tuned circuit. So this is your tuned RF amplifiers, okay? So in a form of a tank circuit. So they resonate at a certain frequency that is dependent on the value of your L and C. Okay? So from our previous discussions, we mentioned that your certain resonance frequency is given by the formula 1 all over 2 pi square root of LC. So depending on the value of your inductor and your capacitor, we can get the value of your resonance frequency here. Okay, so we can get the value for the resonance frequency, and that will be the where your circuit is being tuned. Okay, so let us take for example, it is a radio station. It is tuned to that specific radio station. So for example, 88.9, or for AM, let us say for example 560 kilohertz, or sa 630 kilohertz. So that is your resonance frequency. Okay? So your tuned RF amplifiers, since L and C are both frequency dependent, so we can connect them either using capacitors, capacitive coupling, or either inductors, or what we call transformer coupling. Okay, so no direct coupling, because this two is dependent on a certain cutoff frequency. So this is the definition for a small signal and large signal operation. So small signal operation, the peak-to-peak swing in the collector current is less than 10% of the quiescent collector current, while your large signal operation is the peak-to-peak signal uses all or most of the load line. So for small signal amplifiers, we are usually limited on this smaller portion. Okay, so we will be placing an input signal which is small enough that will be contained only in the middle portion of our active region, while large signal operation is that we will be needing an input signal that can occupy the entire saturation to the cutoff region of your regions of interest. So if we place an input signal this large, so that means it will be functioning on the saturation and cutoff region. So therefore, we are talking about large signal operation. Okay? So most stereo system, they start, okay, they start with a small signal, usually coming from a radio tuner, a tape player, or a compact disc player. Okay, so those input signal is used as the input for a preamp. So therefore, you will be using a preamp because the impedance of those devices is not yet properly matched to your amplifier circuit. So your impedance matching device for that, okay, for your input device and your amplifier circuit, is in a form of a preamplifier. Okay, so your preamplifier there is operating or is functioning as a preamp amplifier. Okay, so it will be connected to a preamp. Okay, and then this is an amplifier that produces a large output, which is already suitable for driving tone or volume controls. Okay? So the signal is then used as the input to a power amplifier. Okay? Because you cannot directly connect your radio tuner or your tape player to a power amplifier. You need an impedance matching at the center or before them, and that is in a form of a preamplifier. Okay, so the output now for your power amplifier produces, okay, so your power amplifier now produces the output power ranging from few hundred milliwatts 200 of watts, and they are now capable of driving your output in a form of your speaker. Okay, so the larger your speaker, the more power it is required for it to sound nicely. Okay, so these are our different classes of operation. Okay, so let us start with class A. So class A operation, the transistor operates in the active region at all times. Okay, so where is your active region? Your active region is at this center. So therefore, the collector current flows for the entire 360 degrees of your AC cycle. So how are we assured that we have a class A operation? Okay, so the designer usually tries to locate the Q point somewhere near the middle of the load line. So this is our load line. If you are the designer for a class A operation, you have to make sure that your Q point is in this point. Okay, so how do you locate your Q point here? So that means we have to place your ICQ here and your VCEQ here so that we are placing our Q point at the center of your load line. Okay, so the signal can swing over the maximum possible range without saturating or cutting off the transistor, because when we reach saturation and cut off, there is a tendency to distort our signal. So one characteristic of a class A amplifier is that it is free from distortion. So therefore, we cannot make use of high input signal to because it may cause distortion. So for class B operation, the collector current flows for only half the cycle or just 180 degrees. So you will only have an output when your input is on the positive half cycle. So when your input is in the negative half cycle, we don't have any output for that. So that means you have only 180 degrees. Okay? So how are we going to design your class B operation? So we're going to place your Q point at the cutoff region. So this is your cutoff region. Okay? So a designer locates your Q point at the cutoff. Only the positive half of the AC base voltage can produce collector current. So, one characteristic for a Class B amplifier is that it reduces heat in power transistors. Okay, so again, we have here a term power transistor. So the usual transistors that we are using from our previous videos, like the 3904 or 3906, they are called small signal transistors, and they are being used for small signal applications. So for power amplifiers, we call them power transistors. Okay, they still have three terminals, still the base collector and the emitter. However, physically, they are much bigger compared to those small signal transistors. Okay, and usually they have heat sink within the component itself. Why? Because they are already capable of producing higher current. So they are bigger because they have to dissipate higher power. Okay, so later you will be using power transistors in one of your laboratory experiments. And then we have your Class C operation. So the Class AB is somewhat operating between Class A and Class B. Okay, so if Class A is at the center and Class B is in this one, so you will be placing your Q point somewhere between the center and the cut off. So you produce your Class AB amplifier. So we will be discussing Class AB amplifier later. Okay? So for Class C, the collector current flows for less than 180 degrees of the cycle. So that means only a part of the positive half cycle of your AC base voltage produces your collector current. So as you can see, we only produce not the entire 180 degrees, but a brief pulses of collector current, only a portion of your positive half. Okay? So later we will be discussing that class C. In designing class C, you usually place your Q point somewhere below your cutoff frequency. Okay, so this explains or this shows the conduction angles for each of these three types of amplifier. Okay, so we have here your input signal. For all the 360 degrees of your input signal, your output is also pure 360 degrees. So as you can see, your output looks exactly like your input here. So what happens is that it is free from distortion. So distortion occurs when your input is not, when your output does not look anymore like your input. Okay, so if there is a clipping or there is a flattening either on the positive half or on the negative half, so we call that distortion. So as you can see, class A is free from distortion because they do look alike. Okay, so in classes of amplifiers, like class in power amplifiers, we're not usually concerned with the amplification. Okay, so our concern here is more on the power that is converted from DC. So it is more on the efficiency and not on the amplification of power. Okay, because power amplification is more of your input AC power versus your output AC power. So for power amplifiers, it is more on efficiency. It is more on the relationship between the AC power developed on the load and the DC input that is being brought about by your DC source. Okay, so no amplification concerned for power amplifiers, unlike from our previous discussion. So as you can see, for class B, it operates only for a 180 degrees. So as you can see, during the negative half cycle, we don't have an output. So as we can see, we have here distortion. So the signal is already distorted. Why? Because your output doesn't look like your input anymore. Okay, and then lastly, you have your class C amplifier, already in a form of a pulses because they conduct in less than 180 degrees. So usually 120 to 150 degrees conduction angle. So therefore, among the three, this has the most distortion. Okay, because your input doesn't really look as your output anymore. Okay, so this is your graphical representation for class A. So as I've mentioned earlier, your Q point is located at the center. So if we placed here an input signal, what happens is that for the positive half, we have here your output. For the negative half, we still have here your output. So this is your output signal. Okay, so you have a conduction, we have an output for the entire 360 degrees of your input signal. And then for class B amplifier, okay, so your Q point is located at the cut off. Okay, so if this is our input signal, we see that during the positive half, we have an output, but during the negative half, we don't have an output anymore. So this is equivalent to 0. So that means you have only an output for the positive duration. And then lastly, for class C, we place your Q point somewhere below your cutoff region. So for the positive input cycle, we only have a portion. Okay, not entire duration of your positive half, just a portion of it. So it is lower than 180 degrees and totally no negative half cycle. So this is for class C amplifier. Okay, so we will be starting with class A amplifier. Okay, so let us analyze class A amplifiers. So Class A amplifiers operates only over the linear region of its load line. Okay, so these are the characteristics for a Class A amplifier. Since the transistor operates over the linear portion of the load line, the output waveform is exactly similar to the input waveform. So when your output waveform is looks like directly as your input waveform, therefore Class A amplifiers are characterized by a high fidelity of the output. So they are used when linearity or freedom from distortion is the primary requisite. Okay, so they are technically free from distortion. But, okay, since its operation is restricted only for a small region of the load line, this amplifier is meant only for amplifying input signal of small amplitudes. Okay, large signals will shift the cue point into the nonlinear region. So where is your nonlinear region? Your saturation and your cutoff. Okay, so it will be producing distortion. And it is not allowed because the number one characteristic is that it should be free from any distortions. Now, so we are just restricted between this specific region. We cannot leave that specific region here. Okay? So, because of that, we are limited to small signals. Okay? We are limited to smaller input signals. Therefore, due to the limitation of the input signal amplitude, your AC power output per active device is very, very small. Okay, so we do not expect a high output when our input is small. So therefore, we are limited to smaller AC output per active device. Okay? So the overall efficiency of the amplifier circuit is given by the AC power delivered to the load. So this is the AC power that was converted divided by the total power delivered by the DC supply. So this is the overall DC power of your circuit. So aside from the overall efficiency, we also have what we call the collector efficiency. So the collector is where your output is being taken. Okay, so if you have a transistor and it is in a common emitter configuration, the output is of course at the collector. So we also have what we call the collector efficiency of the transistor, and is defined as the still the AC power output, okay, that was produced divided by the DC power input that is already within the transistor itself. That means the losses outside the transistor was already deducted. Okay? So the maximum possible collector efficiency for a collector efficiency for a Class A amplifier with a resistive load is actually this is 50%. Okay, so um, there's an error there. Okay, so typo error. So it must be the maximum possible collector efficiency for a Class A amplifier with a resistive load is 50%. Okay, so in case the output transformer is used, the maximum possible overall efficiency and the maximum possible collector efficiency for a Class A amplifier are both 50%. So this is one type of amplifier. So the 25% maximum is for the overall efficiency. Okay, so the 25% maximum theoretical value is for the overall efficiency, but for collector efficiency, it is 50%. Okay, so kindly take down of that. I have, this is wrong, no? So this must be 50%. And this is 25%. But if we will be using a transformer, the overall efficiency can be equal to the maximum possible collector efficiency, which is 50%. Okay, so kindly take down note of this. So for a resistively coupled power amplifier, the maximum theoretical overall efficiency is 25%, while the collector efficiency is 50%. Okay, so let us now discuss the power distribution in a Class A amplifier. Okay, so this is a common emitter configuration and the output characteristic. Okay, so as you can see, this is common emitter configuration because your emitter is the one which is grounded. Okay, so it is within the base that we place your input signal, but our main concern here is the not really the input AC signal, but rather your DC input power. And then from that DC input power, what will be the power that will be converted into AC at this part of your circuit, at the collector part of your circuit. Okay, so this is your VCE, this is your IC, this is DC because it is being provided by your VCC here. Okay, so we will be starting with the total average DC power, okay, drawn by the circuit from the collector battery VCC. And it is given by the formula P in DC. So this is a DC power which is equivalent to VCC multiplied by your ICQ. Again, ICQ is DC. Okay, so if you can still remember, we have discussed how to solve for this ICQ. Now, this total input DC power goes to supply the following. Okay, so upon current passing through RC, this RC here dissipates power right away. Okay, so as you all know, resistors doesn't have only resistance, but it also has power rating. Okay, so there are resistors having 2 watts, 1.5 watts, 1 watt, or even 1/4 watts. Okay, so it is the value of how much power they can dissipate. Okay, so for example, you're having a real circuit. So when you touch this resistor, you can feel it is hot. Okay, so why? Because it dissipated power already. So current flowing across this, and then you have resistance, you produce power here. Okay, so that is in a form of a heat. So heat dissipated by the load resistor RC, which is connected to the collector. And that PR is also a DC power. It is equivalent to RC multiplied by ICQ squared. Okay, so take note, this is DC. So therefore, what is our main concern? Our main concern is AC power. So this DC power is just considered as a loss in a form of a heat. Okay? So, the balance, okay, the remaining from the total power will go to the transistor. So, the power that goes to the transistor will be divided into two. Okay, so the first is your AC power. So we wanted this. This is our purpose. This is our goal, and this is the AC power developed across the load resistor, which constitutes the AC power output. So this is equivalent to I squared RC over or V squared RC. So you always remember that your I here and your V here is in terms of RMS. Okay? So if it is not in terms of RMS, if it is in terms of peak voltage, you have to convert that into RMS. And if peak voltage is given, it is given by VM squared. So it should have square here. So it must be VM squared divided by 2R. Okay, 2RC. So that means we have already converted that into RMS form. Okay, so the remaining is the power dissipated again in the form of heat by the transistor itself, and we call that PC-DC. So if you're going to hold on to the transistor, you can also feel heat. Okay, so that means it also dissipated power. So therefore, out of those all DC powers that we have, we only wanted this, okay, in getting your efficiency. So this is our goal. All DC powers from this formula, they are all losses. Okay? So we have a special case for class A wherein we call it zero signal condition. So when we say zero signal condition, so as we all know, your AC signal is sometimes it has a positive peak, sometimes it is DC or zero, sometimes it has negative peak. So every time your input is zero, okay, this is what we call your zero signal condition. So there is no AC output power, no AC output power that is being produced. So therefore, all the power given to the transistor is wasted as heat. Okay? So, the transistor that you are using must be capable of dissipating this maximum power under zero signal condition. So, in this case, your transistor is dissipating maximum power when your input signal is zero. So, transistor dissipates maximum power under zero signal condition. So, therefore, the rating of your transistor must be enough, okay, to dissipate or to carry this amount of power. Okay, so to summarize, let us say we have a total power. So let us take the maximum value theoretically. So let us say from the total of 100% input DC power, 50% will be from the heat loss, will go to the load resistor as a heat. So this is 50. So the remaining 50 will be delivered to the transistor. So only 25% will be developed, okay, will have the AC power delivered across your load, and the another 25% will again be in a form of a heat loss in the transistor collector region itself. So technically speaking, maximizing the situation, the possible maximum efficiency for a class A amplifier is only 25%. So 50 right away loss, and then from 50 here 25%. So this is already the maximum possible. So we have here 25% efficiency. Okay? So why 50% efficiency for collector? Because for collector, the denominator is this one. So for overall efficiency, the denominator is the whole input DC power. So that's the difference. Okay? So when you have no input signal, the whole 100% input power will just be divided into two. So 50% will go to the load power, to the resistor, power dissipated in the load resistor, and then the DC power being dissipated in the transistor. So 50-50. No AC power is developed. Okay? So for maximum input signal, you have the DC power dissipated in the load, so that is 50%, and then 25% for the average AC power, and then another 25% for the power that is dissipated in the transistor. Okay. So, this is the maximum AC load in power in load. Okay, so we are going to neglect the limitation of cutoff and saturation and assume, at least theoretical, that the voltage and current swings down to zero as possible. Okay, so as you can see, we had your input here, which is already touching your cutoff and your saturation and your cutoff. Okay, so for this, okay, class. For this, so we have here, we assumed here the maximum. Okay, so we assured the maximum AC power in the load. So looking at your current, so our peak to peak is 2 ICQ, and our maximum value or our peak value is ICQ. So to get the AC power, we need to get the RMS value. So how do you get the RMS value? That is the peak value divided by square root of 2. Okay, so the RMS value for your current is ICQ divided by square root of 2. So for the voltage, our peak to peak is 2 VCEQ from the figure. So the maximum peak is your VCEQ. And of course, the RMS is the maximum divided by square root of 2. Okay, so we have here your efficiency is equivalent to POAC divided by P in DC. So VCEQ, POAC is equivalent to the RMS power, the RMS voltage multiplied by the RMS current. So that is VCEQ divided by square root of 2 times ICQ divided by square root of 2. Okay, and then divided by the total input DC, which is ICQ times VCC. But looking at the figure, since we maximize it, your VCC is equal to twice your VCEQ. Okay, so therefore we have here square root of 2 times square root of 2, that is equivalent to 2. Placing that in the denominator and multiplying it by 2 here, your ICQ and your VCEQ will be cancelled out, so giving us 1/4 or 25%. So this is where the 25% maximum theoretical um, values um, is all about. Okay, so as you can see, it is we are expecting a value. Okay, so we are expecting usually a value that is lower than 25%. Okay, so 25% is usually not common because it is a maximum value, and we use a very very large signal there, which is not allowed for class A. So when you are solving class A amplifiers, what do you expect? You expect a value which is always lesser than 25%. Okay? So let's have an example here, a very simple example. A 2N1491 is a power transistor, and it is used in a common emitter amplifier meant for a class A operation. So if its zero signal power dissipation is 10 watts and AC output power is 3.5 watts, find the collector efficiency and the power rating of your transistor. Okay, so if its zero signal power dissipation is 10 watts, so therefore, since zero signal power means the power in the collector region of your transistor when you have no zero signal, so therefore that means this is the power that was delivered to the collector. Okay, so this is the power, the total power that was delivered to the transistor. In that case, we can solve for the collector efficiency as So we can solve for the collector efficiency as POAC, which is your AC output power, 3.5, divided by the power that was delivered to the transistor. So this is not the total input power. This is not the total input DC power. This is just the power that was delivered to the transistor. How did we know that? Because that is the zero signal power dissipation. And when we have zero signal power dissipation, that means no AC was created when we read 10 watts at the collector. So therefore, we have a collector efficiency of 0.35 or 35%. So you might be wondering, is this acceptable? Yes, because the ideal or the maximum value for the collector efficiency is 50%. So therefore, the collector efficiency of 35% is acceptable or a possible answer. So what is not acceptable if this is greater than 50%? Okay, so since zero signal condition represents worst case condition for the transistor, it means that all the 10 watts power is dissipated by it because no AC AC power was converted. So therefore, the collector power rating must be 10 watts because at zero signal power, it will experience a power or a heat or a power contribution of 10 watts. So therefore, the type of transistor that you are using must have a power rating of at least 10 watts. Because if you use 5 watts transistor for this and for zero signal power, it receives 10 watts. Therefore, your transistor will be destroyed. So therefore, it must be 10 watts or at least or much better, greater than 10 watts. Okay? So let's have another example. For a Class A amplifier, Class A common emitter amplifier, VCEQ is 10 volts and ICQ is 500 milliamperes. Okay, so in our previous topics, we usually solve for VCEQ and we usually solve for ICQ. So in this case, it is already given. And as you can see, 500 milliamperes is a very, very big current compared to those we have previously solved. So previously, we are just solving for around lesser than 5 milliamperes or even microamperes. Okay, so why do we have 500 milliamperes here? Because technically we are now discussing power amplifiers. So we're going to assume that the transistor that was used here is a power transistor that is capable of handling 500 milliamperes. Okay, so if the collector output current varies for by about plus or minus 250, so therefore we have an input signal because your current is varying plus or minus 250 milliamperes, okay, when an input signal is applied at the base. So we have to compute for the following. Okay, the total DC power taken by the circuit, the DC power dissipated by the collector load, the AC power developed across the load, the power delivered to the transistor, the DC power wasted in the transistor collector, the overall efficiency, and the collector efficiency. So usually these are the important things that is being asked for a power amplifier problems. So for the input DC power, that is your source, which is your VCC multiplied by your ICQ, that means 10 watts, okay? So for PRDC, that is ICQ squared times RC, so that will give us 5 watts. So imagine, okay, out of those 10 watts, 5 watts was already delivered from for the resistor, and this is already a waste. So this is already a loss. So this is very so it is very impossible really to have a lossless system because all of the resistors in your circuit is dissipating power. So therefore, they have a contribution to the total input DC power. Okay, now we want this. Okay, so your power AC is I squared RC. However, this I here must be in terms of RMS value. Now, the maximum value of your output AC current is 250 milliamperes because it says in the problem it varies from positive 250 to negative 250. So it is 500 milliamperes peak to peak or 250 milliamperes peak. Hence, in getting the RMS value, we have to divide your peak value, which is 250 milliamperes, divide by square root of 2. Okay? So, this RMS current now, we square it and then multiply it with the resistance. That will give us 0.625 watts. So, imagine, okay, out of the 10 watts, okay, out of that 10 watts, 5 watts is lost. 5 watts is delivered to the transistor, and out of that 5 watts that was delivered to the transistor, only 0.625 watts was converted into AC power. Okay, so we expect that we have a low efficiency in this type of amplifier circuit. So the total power that was delivered to the transistor is simply 10 watts minus 5 watts because this is delivered to the load resistance. So we have here 5 watts. Okay? And since out of this 5 watts, 0.625 was delivered or was converted into AC, so the power that was dissipated by your collector or your transistor in the collector region is simply the difference between 5 watts and 0.625, and this is 4.375 watts. Okay, so in getting the overall efficiency, that is 0.625 divided by 10, so that will only give us 6.25%. Okay, very, very low, but is expected. Why? Because it is below 25%. So if you have a value that is higher than 25%, so you really have to repeat your computation because for Class A amplifier, the maximum is 25%. Okay, so this is 12.5. So the maximum for collector efficiency is 50%. So why? Because in the denominator, we will just be using that power that was delivered by the transistor already. So this is just divide by 5. So this will give you 12.5%. Okay? So, how much must be the rating of your transistor? So, your transistor must at least have a rating of 5 watts because at zero condition, 0.625 will not be produced. So, all of the 5 watts is dissipated by your transistor. So, its power rating must at least be equal to 5 watts or better, greater than 5 watts. Okay? So, from that problem, we see that right away half of your power is already lost in the resistor. Okay, so let us do something about that. We have here still class A, but this time this is transformer coupled amplifier. Okay, so we have a large amount of DC power that the resistive load in the collector must dissipate. So this is used. Okay, so we use a suitable transformer for coupling the load to the amplifier stage. So as you can see from the figure, your load resistance is not directly connected to your transistor. Okay, therefore your current IC here will not directly flow across your load resistance here. Okay, so load is not directly connected to the collector terminal, and the DC current therefore that not pass through it. Okay, so ideally, okay, for ideal transformers, your primary winding resistance is 0. So therefore, if your primary winding resistance is 0, you have a DC power loss in the load. Okay, so the DC power loss in the load is actually 0. Unlike earlier, it was already 50% of your total power input. Okay, but a real transformer, okay, in actual, okay, so a small DC resistance of the primary winding which does absorb some power, though much less than direct coupled load. Okay, so it's just like we are substituting an AC load in place of an ohmic or DC load. Okay, because your transformer is in the form of a AC load, which is it is an inductance. Okay. So your secondary load RL, when referred to primary, it becomes RL prime. Okay, so RL prime is equivalent to RL divided by K squared. So we can either use the K, voltage transformation ratio, which is equivalent to the secondary winding divided by the primary winding, or the secondary voltage divided by the primary voltage. Or we can make use of your turns ratio, or your turns ratio is just the reciprocal of your voltage transformation ratio, or this is equivalent to the primary winding divided by the secondary winding. Okay, so in this case, it is just like that your RL can be made to look much bigger than what is its actual value is. Okay, so for an ideal transformer, since there is no primary voltage drop, therefore all of your VCC is equivalent to VCEQ because no drop across your resistor. So all the power being supplied by VCC is delivered to the transistor. So it is now possible to have a collector efficiency and an overall efficiency which are equal with each other. Okay, so how do we prove it? So how do we prove it? Okay, so we have here, so your VCEQ now is equivalent to your VCC. Okay, so your P in DC is equivalent to VCC multiplied by your ICQ already. So earlier, we have here 2 VCEQ. Okay, so this time it is VCC times ICQ. So for the whole of the power is given to the transistor. Therefore, your RMS voltage, instead of using VCE, we use VCC because they are just equal. So we have here VCC divided by square root of 2. So the RMS current, so this is not voltage, so the RMS current is equal to ICQ divided by square root of 2, giving us your POAC. Okay, POAC equal to the RMS voltage and RMS current product. Okay, and that will give you VCC ICQ divided by 2. Okay, so to get the power efficiency, we have here POAC divided by P in DC. So this is VCC ICQ over 2 divide by VCC ICQ. So VCC and ICQ will be cancelled out, giving us 1 half or 50%. So 50% is still low, but it is better than 25%. Okay? And again, I'll repeat, this is for maximum or theoretical values only. So in reality, we are expecting values that is always lesser than 50%. So this is possible if you use class A power amplifier with transformer. Okay? But if we're using the resistive load, our maximum efficiency is still at 25%. Okay? So this is your derivation. Okay? So hence the maximum value of the overall efficiency is 50%. So the collector efficiency is now equal to the overall efficiency. Okay? So we have here an example. The optimum resistance for a certain transistor is 200. Okay? So this is already your RL prime, the optimum resistance. So the smaller resistance that was made to look much bigger. Okay? So what is the turns ratio or A? N1 is to N2, primary winding over secondary winding of a transformer required to couple an 8 ohm. Okay, so the actual load is an 8 ohm loudspeaker to the transistor. So RL prime is equivalent to A squared RL. So that is 200 is equal to A squared multiplied by A. So A is equal to 5. So that means 5 is to 1. So what do we mean by 5 is to 1? So A is equal to N1 all over N2. So this is 5. So therefore, that is 5 is to 1. So what does that mean? That means you are using a 5 is to 1 step-down transformer. Okay, so the required transformer to be used is a 5 is to 1 step-down transformer. So for a transformer coupled optimally, okay, so the term optimally here means we can use the maximum value. Okay, so when you hear the word maximum or optimal, that means we are safe to use the maximum value. Okay, so we have here for an optimally biased class A amplifier shown in the figure, we have to find the following. So the transformer turns ratio, what type of transformer that we're going to use. Is it a step up? Is it a step down? Okay, so it depends on the transformer turns ratio. So the collector current and the transistor power rating. Okay, so here is our circuit. Your VCC is 30 volts. We have here your primary winding. We have your primary side. We have here your secondary side. We have here your RL. It is equivalent to 4 ohms. We have here your power across your load. So that is 4.5. So it is not 4 to 5. It's 4.5 watts. Okay. So our solution is we have to solve for V2, which is the RMS secondary voltage. Okay. So how do we solve for V2? We are given the load power, okay, or POAC power. So that is the converted power to the load. So that is equivalent to V squared all over RL in terms of RMS. That is equivalent to the maximum or peak secondary voltage divided by square root of 2 squared divided by RL. Or we can have there so we have here 2 VM secondary secondary peak voltage squared divided by 2 RL. Okay? So equating that to our formula, so the maximum value at the secondary stage is equal to the square root of 2 times R times your POAC. So substituting the value, we get the secondary voltage be equal to 6 volts. Okay? So now your peak value for the primary voltage is, so since this also represents the peak collector voltage, and for optimally biased circuit, the peak value of your collector emitter voltage is equal to 30 volts. Okay? So your primary is 30, so multiplied by the secondary, which is 6, so we can solve for A. So what is A? A is equal to 5. Again, that is a step-down transformer with turns ratio of 5 is to 1. So from 30 volts to 6 volts. So the 30 volts was stepped down to 6 volts at the secondary. Okay? So the overall efficiency is 50%. So why did we use 50%? Because it says in the problem that it is optimal. So we can safely use 50%. So why 50%? Because we are transformer coupled. Okay? So 50%, hence for the load power of 4.5. So PO efficiency is POAC divided by P in DC. So we can use 50% here. Okay, so if this is 50% and the output AC power is 4.5, therefore we can get the total input DC power, which is equal to 9 watts. Okay, so using your VCC equal to 30 and then your P in DC equal to 9 watts, we can solve for your collector current, which is equivalent to 300 milliamperes. Actually, we are just using the power formula and the efficiency formula class. So there is no new formula, just the efficiency. Okay? So for worst case condition for the transistor, okay, is when there is no input signal. So in that case, all of the 9 watts will be delivered to the transistor. So in that case, okay, so your transistor has to dissipate that entire input power. So therefore, the transistor power rating to be used must be 9 watts. Okay, so that's it. Okay, so our next is Class B amplifier. So I will just be discussing Class B amplifier on the next video. Okay, so thank you very much for watching and don't forget to like. Okay, so goodbye for now and God bless. Bye.